subscribe and click the bell icon to turn on notifications.
Hello everyone, and welcome to our course, Introduction to Analytics, a course that will give you an overview of the field of analytics, as well as a detailed explanation of what is going on with today's most exciting technology. My name is Andrew Pearson, and I am the founder and managing director of Intelligentsia Limited, a software and AI consulting company based in Macau and Hong Kong. To give you a historical perspective on the subject, I will touch upon developments that have occurred over the past few hundred years, but I will spend the bulk of the time discussing the analytics that are in use today, specifically artificial intelligence, AI, machine learning, ML, and deep learning, DL, three technologies that seem to be everywhere today. In section 1, I will start off with a history of analytics. Then I will do an introduction to data and big data, data mining. We'll delve into the CRISP-DM and SEMA data mining methodologies. Business intelligence refers to the tools, technologies, and practices that organizations use to gather, store, access, and analyze data to make better informed business decisions. Data visualization is another term for it, and I will showcase the 14 principles that will ensure your dashboards are surfacing your data in the most visually compelling way. A session on the 4 types of analytics follows, and section 1 concludes with a session on non-AI types of analytics. Section 2 starts with a deep dive into AI, which takes 2 different sessions, as does the next subject, machine learning. Session 5 rounds out the AI discussion with deep learning, which explains in deep detail what a neural net is. Sessions on the many types of AI and machine learning modeling types round out the course. There's a lot of information here, and the best way would be to take it all in. Don't get too bogged down in the details. Keep track of what interests you so you can further your development in those areas. This course should be particularly interesting for executives who will be working with AI and maybe not getting involved with the actual model build. That being said, anyone who does want a career building models will get a nice introduction to the world of analytics, its past history, and potential future. So I'll see you in lesson 1. The history of analytics begins in 1663 when John Graunt, the founding father of demography and vital statistics, analyzed data to make sense of deaths caused by an outbreak of the bubonic plague in London. He was the first to use descriptive statistics presenting mortality in terms of survivorship. In 1786, William Playfair, a Scottish engineer, created the first bar chart presenting categorical data in rectangular bars with heights and lengths proportional to the values of the data set. They are still in wide use today. In 1865, Richard Millar Devons coined the term business intelligence to describe the process of analyzing and utilizing data to deliver actionable intelligence for a business. In 1902, Italian scientist Guglielmo Marconi patented a magnetic detector which became the standard wireless receiver for years to come. In 1926, Nikola Tesla predicted humans would one day have a device that fit into a vest pocket which allowed access to huge amounts of data through wireless technology. In 1928, Fritz Flumer invented a process allowing data to be encrypted on magnetic papers. This led to the creation of magnetic tape, the foundational technology for music and video cassettes as well as movie reels. In 1943, codebreakers at England's Bletchley Park created Colossus, a theoretical computer that analyzed massive amounts of data and broke Germany's encrypted war codes. These developments were instrumental in the defeat of the Nazis during World War II. After World War II, AI flourished during its first golden age. Researchers wanted to discover if computers could learn without being explicitly programmed. In John McCarthy's 1955 letter to the editor of MIT's Tech Review, the term artificial intelligence was first used in print. In the late 1950s, Frank Rosenblatt, an American psychologist, introduced the perceptron, the idea of a device that mimicked the neural structure of the human brain and showed the capacity to learn. Ensuing research, however, has revealed the perceptron has very limited ability. In 1956, the Dartmouth Conference convened, bringing together the first conference of researchers to discuss whether it was even possible for computers to think like humans. In 1957, Marvin Minsky, a man dubbed the father of AI, received funding from the U.S. Army, launching his decades-long research into AI at MIT. In 1958, Minsky published the influential paper, A Proposal for the Study of General Intelligence, proposing the Minsky thesis, a framework for thinking about how people learn and make decisions based upon their experience. It has since become known as the theory of knowledge. In 1959, Minsky founded MIT's AI Lab, where many of the early advances in AI occurred. In 1959, Arthur Samuel, an early AI pioneer, coined the term machine learning. Between 1957 and 1974, AI flourished thanks to new data, more efficient storage techniques that made data more accessible. During this time, the U.S. government invested heavily in AI, funding several research institutions through the Defense Advanced Research Projects Agency. However, even though optimism was high, the AI tools weren't quite up to the task because of the high demands of this promising field. 1961, Marvin Minsky founded the MIT Artificial Intelligence Laboratory, which was funded by the U.S. Department of Defense, giving it a level of autonomy and backing greater than most academic institutions. Minsky's focus evolved from pure research to practical applications. Teaming up with John McCarthy on what would become known as artificial intelligence, the two developed one of the earliest computer programs capable of playing tic-tac-toe. In 1965, the U.S. government created the first data center to store millions of tax returns and fingerprints on magnetic tape. In the mid-60s, Intel's Gordon Moore proposed Moore's Law, which projected that the number of transistors on a computer chip would double every 18 months, meaning each new generation of the chips could deliver twice the processing power as previous chips, but at the same price. In 1966, the MIT Artificial Intelligence Laboratory produced the first chatbot, ELIZA. In 1969, Advanced Research Projects Agency Network, the first wide-area network that included distributed control and TCI IP protocols, was created. This formed the foundation of today's Internet. In 1969, Marvin Minsky published The Society of Mind, proposing the idea that people learn through experience, the principles of which can be used to build intelligent machines. In 1970, Edgar F. Codd, an IBM mathematician, revealed how information stored in a large database could be accessed without knowledge of where it resided or how it was structured. These relational databases, as they would become known, allowed users to write in SQL and gained popularity in the 1980s because they allowed data to be analyzed on demand. Between 1974 and 1980, the first AI winter descends. The lack of computational power was hampering development in the field. Data couldn't be stored or processed fast enough, so funding dried up and research stalled. On January 1st, 1983, the Internet was born. Computers shared data on a scale never before seen in history, and the information age begins. In the 1980s, interest in AI reignites after an expansion of the algorithmic toolkit, as well as an increase in government and venture capitalist funding. Throughout the 80s, John Hopfield and David Rumelhart popularized the deep learning modeling technique. Although the concept of deep learning had been around since the 1950s, Hopfield and Rumelhart's research showed how computers learn from experience. In the 80s, Edward Feinbaum introduced expert systems which mimic the decision-making process of a human expert. In 1986, David E. Rumelhart, Jeffrey E. Hinton, and Ronald J. Williams introduced backpropagation in their paper Learning Representations by Backpropagating Errors. Between 1987 and 1993, a second AI winter descends upon the field as the early promise of AI falls short of expectations. However, government bureaucrats, venture capitalists, and researchers continue to make advances despite the criticism. In 1989, Gartner's Howard Dresser coins the term business intelligence to represent the ability of companies to make better business decisions by utilizing and analyzing the data stored in their organization's databases. On September 1st, 1992, Jeffrey Hinton publishes his seminal work, How Neural Nets Learn from Experience. The article reveals how networks of artificial Neurons can learn to represent complicated information, which provides insight into the learning abilities of the human brain. In 1997, IBM's Deep Blue, a chess-playing computer program, beats reigning world chess champion Garry Kasparov, proving an AI decision-making program can defeat the best humankind has to offer. On September 15, 1997, Google registers Google.com, officially launching it a year later. Google becomes synonymous with search. In 1997, Jürgen Schmidhuber and Sepp Hochreiter introduced a novel, efficient, gradient-based deep learning method called long short-term memory that can learn tasks requiring a memory of events that took place thousands of discrete steps earlier. It is the basis for much of today's speech recognition training work. In 1998, Jan LeCun, Patrick Hafner, and Joshua Bengio published their paper Object Recognition with Gradient-Based Learning, defining the concept of convolutional neural networks, revealing how CNNs mimic the human visual cortex by using neural networks to recognize multiple objects without requiring explicit segmentation of the objects from their surroundings. In 1998, Carlo Strozzi developed NoSQL, an open-source database that stores, retrieves, and models data in documents rather than in a standard relational tables way. In April 1998, John Massey, chief scientist at SGI, presents the paper Big Data and the Next Wave of Infra-Stress Problems, Solutions, Opportunities at a Usenix conference, introducing the term big data for the first time. Throughout the 90s, data mining, the process of discovering patterns hidden within large datasets, is embraced by the business community, helping them optimize their business processes as well as better predict their customer needs. In 1999, Salesforce provides one of the first cloud-based on-demand CRM systems, and it quickly gains traction in the market. In 2001, Doug Lanny, an analyst for Gartner, coins the 3 V's: volume, variety, and velocity, defining the dimensions and properties of big data. In 2005, computer scientists Doug Cutting and Mike Caffarella created Apache Hadoop, the open-source framework used to store and process massive data sets. 2006, Amazon Web Service, AWS, offers web-based computing infrastructure services. Between 2011 and 2014, Apple's Siri, Google's Google Now, and Microsoft's Cortana are released. They use NLP to answer questions and make recommendations. In 2011, IBM's Watson defeats 2 Jeopardy champions. In 2012, Alex Krizhevsky, Ilya Sutskever, and Geoffrey Hinton reveal the power of deep learning by showing significant results in a prominent ImageNet competition. 2012 and 2013 saw breakthrough work on large-scale image recognition at Google Brain, which was led by Jeffrey Dean and Andrew Ng, which they documented in their paper, Large-Scale Distributed Deep Networks. In June 2014, Ian Goodfellow publishes his paper on Generative Adversarial Networks. GANs can mimic training datasets, then create new data with similar characteristics to the training data. In 2014, Facebook develops DeepFace, an algorithm that recognizes individuals in photographs as accurately as humans do. The same year, Richard S. Sutton and Andrew G. Bartow release Reinforcement Learning, an Introduction, a work that brought together key deep learning ideas and algorithms. In March 2016, Google's AlphaGo wins the Google DeepMind Challenge match, a 5-game Go match between top Go player Lee Sedol and AlphaGo, an AI program developed by Google DeepMind. In 2018, Alibaba Language Processing AI outscores humans in a Stanford University reading and comprehension test. 2018, Google develops BERT. This technology allows anyone to train their own state-of-the-art question answering system. In 2018, Google releases Duplex. This language model generates text by adopting algorithms that are pre-trained, i.e., which have already been fed the data required for task execution. In 2020, OpenAI GPT-3 is introduced. It is a state-of-the-art language processing AI model developed by OpenAI, and it is capable of generating human-like text and has a wide range of applications, including language translation, language modeling, and generating text for applications such as chatbots. In 2020, Microsoft introduced its Turing Natural Language Generation T-NLG, which was then the largest language model ever published at 17 billion parameters. Now that I've laid out the timeline for you, please go to the next course, 1-02, Introduction to Data and Big Data. It is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. The Sherlock Holmes line is as good as any tech CEO's quote to explain the importance of data, which should be the foundation of any research and/or analysis. Without it, facts can be twisted, ideologies shoehorned to fit assumptions, and theories tailored to fit false narratives. It's important to get data right by analyzing it properly, but it all starts with the getting of the data in the first place. So what exactly is this thing we call data? In English, data is the plural form of the Latin word datum, which means a given, or that which is taken for granted and used as the foundation of computations. In general, data is information, essentially facts or numbers, collected to be examined and considered and used to help decision-making, or information in an electronic form that can be stored and used by a computer. There are many ways to classify data, and the specific types of data that are used will depend on the context and the application using that data. However, one common classification scheme divides data into three main categories. Structured data is organized and formatted in a predictable and well-defined way, typically using a formal data model or schema. Examples of structured data include relational databases, tabular data, and XML documents. Structured data is typically easy to process and analyze because the structure of the data is well-defined and predictable. Unstructured data is data that does not have a predefined structure or format. Examples of this type of data include text documents, images, audio and video files, and social media posts. Unstructured data is often more difficult to process and analyze because it does not have a well-defined structure or schema. Semi-structured data is data that has some structure, but not as much as fully structured data. Examples of semi-structured data include JSON documents and HTML pages. Semi-structured data is typically easier to process and analyze than unstructured data because it has some inherent structure, but it can still be more challenging than fully structured data. Overall, these three types of data represent different levels of structure and organization, and each has its own strengths and limitations. The specific type of data that is used will depend on the application and the needs of the user. Semi-structured data is typically stored in a file system or a NoSQL database, and it can be organized and analyzed with the help of software tools. Big data is large amounts of data that are too complex and voluminous to be analyzed using traditional methods. It has revolutionized how businesses and governments store and process information, allowing them to make more informed decisions, analyze trends, and develop new products and services. The term big data first came into use in the late 1990s. In 2001, Doug Laney coined the 3 V's, volume, variety, and velocity, defining the dimensions and properties of big data. Volume. Organizations collect data from a variety of sources, including from transactions, smart devices, industrial equipment, videos, images, audio, social media, and more. Velocity. With the growth in the IoT, data streams into businesses at an unprecedented speed and must be handled in a timely manner. Variety. Data comes in all types of formats, from structured numeric data in traditional databases to unstructured text documents, emails, videos, audios, and financial transactions. The 3 V's soon expanded to 6 V's, with veracity, the degree to which big data can be trusted, value, the business value of the data collected, and variability, the way in which big data can be used and formatted. Big data has grown to include things like veracity, validity, volatility, variability, venue, vocabulary, vagueness, and versatility. Big data is huge and growing, and I'll explain in the next session how data mining is being used to wrangle and understand this data, but for now, understand the use cases are growing by the day. Combining big data with high-performance analytics can help with root cause analysis, risk management, fraud detection, and AI and ML and deep learning. According to SAS, big data is important because it can help streamline resource management, improve operational efficiency, optimize product development, drive new revenue and growth opportunities, as well as enable smart decision-making. For healthcare providers, it can improve patient care, identify which treatments are most effective for certain conditions, reduce healthcare costs overall, personalize medicine, develop new treatments, and improve public health. For finance companies, it can help with fraud detection, risk management, customer segmentation, personalization marketing, as well as help with overall operational efficiency. For retailers, it can help with pricing optimization, fraud and flaw detection, supply chain logistics, personalization marketing, labor utilization, as well as helping improve overall efficiency. For telcos, it can optimize the quality of service, prevent revenue leakage, reduce customer churn, allow data monetization, fraud detection, and personalization marketing. As the technology continues to evolve, big data will become an even more important tool for businesses and governments going forward. We started this session with a quote from Sherlock Holmes that warned about making assumptions before one has data. In the next session, which is about data mining, I will delve into a little history of data mining, as well as introducing you to the differing data mining models that are available to you, each in their own way trying to find a truth in the data that will provide reliable and useful analytics. Data mining. According to SAS, data mining is a cornerstone of analytics, helping you develop the models that you can uncover connections within millions or even billions of records. IBM considers data mining, also known as knowledge discovery and data, KDD, as the process of uncovering patterns and other valuable information from large data sets. Data mining is the process of extracting meaningful patterns from large data sets. It is an important process in discovering valuable information from the vast amounts of data stored in a database, and it is an important tool for making decisions in many different fields. The earliest use dates back to the early 1800s, when statisticians and mathematicians began to use statistical methods to analyze data. By the early 20th century, computers had become a necessity in the field of mathematics and statistics, and data mining began to gain traction as a viable tool for analyzing data. In the 1950s, data mining techniques were developed to help businesses make better decisions by uncovering hidden patterns in their data. In terms of a timeline, in the 1960s, the development of powerful computers and the introduction of the first database systems allowed for the further development of data mining techniques. In the 1970s, data mining began to be used for more than just business decisions. It was used for scientific research, for the study of social phenomenon, and for the prediction of future trends. By the 1980s, data mining had become an important tool for a wide range of applications, from marketing to financial services. By the 1990s, the development of the Internet enabled the use of data mining on a much grander scale. In 2001, Doug Lanny, an analyst with Gartner, coined the 3 V's, defining the dimensions and properties of big data. In 2005, computer scientists Doug Cutting and Mike Caffarella created Apache Hadoop, the open-source framework used to store and process large data sets. In 2006, Amazon Web Services offers web-based computing infrastructure services. 2010, the field of deep learning, which involves using neural networks to process large amounts of data, becomes a major area of focus in AI research. SAS believes data mining comprises of 3 intertwined scientific disciplines: statistics, the numeric study of data relationships; artificial intelligence, human-like intelligence displayed by software and/or machines; and machine learning, algorithms that can learn from data to make predictions. For SAS, data mining allows users to sift through all the chaotic and repetitive noise in a dataset, understand what is relevant, and then make good use of that information to assess likely outcomes, and accelerate the pace of making informed decisions. For IBM, the data mining process involves a number of steps from data collection to visualization that allow for the extraction of valuable information from large data sets. IBM claims there are 4 main steps to data mining, including set the business objectives, Although this can be the hardest part, many organizations don't spend enough time on this vital step. Data scientists and business stakeholders need to work together to define the business problem, which helps inform the data questions and parameters for a given project. Analysts may also need to do additional research to understand the business context appropriately. Data preparation. Once the problem's scope has been defined, it is easier for data scientists to identify which set of data will help answer the pertinent questions to the business. Once they collect the relevant data, the data will be cleaned, removing any noise such as duplicates, missing values, and outliers. Depending on the data set, an additional step may be taken to reduce the number of dimensions, as too many features can slow down any subsequent computation. Data scientists will look to retain the most important predictors to ensure optimal accuracy within any models. Model building and pattern mining. Depending on the type of analysis, data scientists may investigate any interesting data relationships, results evaluation, knowledge implementation. Once the data is aggregated, it's time to evaluate and interpret the results, which should be valid, novel, useful, and understandable. When this criteria is met, organizations can use this knowledge to implement new strategies, achieving their intended data mining and analytics objectives. In his paper, The CRISP-DM Model, the New Blueprint for Data Mining, Colin Shearer introduces the concept of the Cross-Industry Standard Process for Data Mining, which is more commonly known by its acronym CRISP-DM. It is a data mining process model that describes commonly used approaches that data mining experts use to tackle problems. It is currently the de facto standard for developing data mining and data discovery projects. The process has 6 steps: business understanding, determining the business objectives. Understanding a client's true goal is critical to uncovering the important factors involved in the planned project and to ensuring that the project does not result in producing the right answers to the wrong questions. To accomplish this, the data analyst must uncover the primary business objective as well as the related questions the business would like to address. Questions such as, what is the background to the project? What are the business objectives? And what is the business success criteria? To start with, businesses must assess the situation. In this step, the data analyst outlines the resources, from personnel to software, that are available to accomplish the data mining project. Particularly important is discovering what data is available to meet the primary business goal. At this point, the data analyst also should list the assumptions made in the project. Assumptions such as, to address the business question, a minimum number of customers over age 50 is necessary. During this section, the data analyst should list the project risks, list potential solutions to those risks, as well as create a glossary of business and data mining terms and construct a cost-benefit analysis for the project. Determining the data mining goals. State project objectives in business terms such as predict how many widgets a customer will buy given their purchases in the past 3 years, demographic information, age, salary, city, etc., and the item price. Success also should be defined in these terms. For instance, success could be defined as achieving a certain level of predictive accuracy. If the business goal cannot be effectively translated into a data mining goal, it may be wise to consider redefining the problem at this point. Produce a project plan. The project plan describes the intended plan for achieving the data mining goals, including outlining specific steps and a proposed timeline, an assessment of potential risks, and an initial assessment of the tools and techniques needed to support the project. Within the industry, generally accepted timeline standards include 50 to 70% of the time and effort in a data mining project involves the data preparation phase. 20 to 30% involves the data understanding phase. 10 to 20% is spent in each of the modeling, evaluation, and business understanding phases. And finally, 5 to 10% is spent in the deployment planning phase. The next phase is the data understanding phase. This stage starts with an initial data collection. The analyst then proceeds to increase familiarity with the data, to identify data quality problems, to discover initial insights into the data, or to detect interesting subsets to form hypotheses about hidden information. The data understanding phase involves 4 steps, including the collection of the initial data, the description of data, the exploration of data, and the verification of data quality. Collecting the initial data. Here, a data analyst acquires the necessary data, including loading and integrating this data if necessary. The analyst should make sure to report problems encountered in his or her solutions to aid with future replications of the project. For instance, data may have to be collected from several different sources, and some of these sources may have a long lag time. It is helpful to know this in advance to avoid potential delays. Describe the data. During this step, the data analyst examines the gross or surface properties of the acquired data and reports on the results, examining issues such as the format of the data, quantity of the data, the number of records and fields in each table, the identities of the fields, and any other surface features of the data. The key questions to ask: does the data acquired satisfy the relevant requirements? Explore the data. This task tackles the data mining questions, which can be addressed using querying, visualization, and reporting. For instance, a data analyst may query the data to discover the types of products that purchasers in a particular income group usually buy, or the analyst may run a visualization analysis to uncover potential fraud patterns. The data analyst should then create a data exploration report that outlines first findings or an initial hypothesis and the potential impact of the remainder of the project. Verify data quality. At this point, the analyst examines the quality of the data, addressing questions such as: is the data complete? Missing values often occur, particularly if the data was collected across long periods of time. Some common items to check include missing attributes and blank fields, whether all possible values are represented, the plausibility of values, the spelling of values, and whether attributes with different values have similar meanings. Produce a project plan. The project plan describes the intended plan for achieving the data mining goals, including outlining specific steps and a proposed timeline, an assessment of potential risks, and an initial assessment of the tools and techniques needed to support the project. Deliverables for this phase include initial data collection report, data description report, data exploration report, and a data quality report. I will continue the discussion of CRISP DM and the SEMA method in the Data Mining Part 2 session. Data Mining Part 2. Data Preparation. The data preparation phase covers all activities to construct the final data set or the data that will be fed into the modeling tools from the initial raw data. Tasks include table, record, and attribute selection, as well as transformation and cleaning of data for modeling tools. Deciding on the data that will be used for the analysis is based on several criteria, including its relevance to the data mining goals, as well as quality and technical constraints such as limits on data volume or data types. Part of the data selection process should involve explaining why certain data was included or excluded. Clean data. Without clean data, the results of a data mining analysis are in question. Thus, at this stage, the data analyst must either select clean subsets of data or incorporate more ambitious techniques, such as estimating missing data through modeling analysis. Construct data. After the data is cleaned, the data analyst should undertake data preparation operations such as developing entirely new records or producing derived attributes. An example of a new record will be the creation of an empty purchase record for customers who made no purchases during the year. Derived attributes, in contrast, are new attributes that are constructed from existing attributes such as area equals length times width. These derived attributes should only be added if they ease the model process or facilitate the modeling algorithm, not just to reduce the number of input attributes. Integrate data. Integrating data involves combining information from multiple tables or records to create new records or values. With table-based data, an analyst can join two or more tables that have different information about the same objects. Data integration also covers aggregations. Aggregations refer to the operations where new values are computed by summarizing information from multiple records and/or tables. Format data. In some cases, the data analyst will change the format or design of the data. These changes might be simple, for example, removing illegal characters from strings or trimming them to a maximum length, or they may be more complex, such as those involving a reorganization of the information. For this phase, the tasks and outputs could be dataset descriptions, rationale for inclusion/exclusion, data cleansing report, and a report on constructed data, merged data, and reformatted data. In the data modeling phase, various modeling techniques are selected and applied, and their parameters are calibrated to optimal values. Typically, several techniques exist for the same data mining problem type. Some techniques have specific requirements on the form of data. Therefore, stepping back to the data preparation phase may be necessary. The steps include select the modeling technique. This task refers to choosing one or more specific modeling techniques, such as decision tree building or neural network generation with backpropagation. If assumptions are attached to the modeling technique, these should be recorded. Generate test design. After building a model, the data analyst must test the model's quality and validity, running empirical testing to determine the strength of the model. Typically, the data is separated into the train and test set. The model is built on the training set, and its quality is estimated on a separate test set. This enables the data analyst to measure how well the model can predict history before using it to predict the future. Build a model. After testing, the data analyst runs the modeling tool on the prepared data set to create one or more models. Assess the model. The data mining analyst interprets the models according to his or her domain knowledge, the data mining success criteria, and the desired test design. The data mining analyst judges the success of the application of modeling and discovery techniques technically, but he or she should also work with business analysts and domain experts in order to interpret the data mining results in the business context. Evaluation. Data preparation. Before proceeding to final deployment of the model built by the data analyst, it is important to more thoroughly evaluate the model and review the model's construction to be certain it properly achieves the business objectives. Here it is critical to determine if some important business issue has not been sufficiently considered. At the end of this phase, the project leader should then decide exactly how to use the data mining results. Evaluate results. This step assesses the degree to which the model meets the business objectives and determines if there is some business reason why this model is deficient. Another option here is to test the models on real-world application, if time and budget constraints permit. Moreover, evaluation also seeks to unveil the additional challenges, information, or hints for future direction. Review process. It is now appropriate to do a more thorough review of the data mining engagement to determine if there is any important factor or task that has somehow been overlooked. This review also covers quality assurance issues. For example, did we correctly build the model? Did we only use allowable attributes that are available for future deployment? Determine next steps. At this stage, the project leader must decide whether to finish this project and move on to deployment, or whether to initiate further iterations or set up new data mining projects. Deployment. Model creation is generally not the end of the project. The knowledge gained must be organized and presented in a way that the customer can use it, which often involves applying live models within an organization's decision-making processes, such as the real-time personalization of web pages or repeated scoring of marketing databases. It is important for the customer to understand upfront what actions must be taken in order to actually make use of the created models. Plan deployment. In order to deploy the data mining results into the business, this task takes the evaluation results and develops a strategy for deployment. Plan monitoring and maintenance. Monitoring and maintenance are important issues if the data mining result is to become part of the day-to-day business and its environment. A carefully prepared maintenance strategy avoids incorrect usage of data mining results. Produce final report. Depending on the deployment plan, this report may be only a summary of the project and its experiences, if they have not already been documented as an ongoing activity, or it may be a final and comprehensive presentation of the data mining results. Review project. The data analyst should assess failures and successes as well as potential areas of improvement for use in future projects. This step should include a summary of important experiences during the project and can include interviews with the significant project participants. Review project. This document could include pitfalls, misleading approaches, or hints for selecting the best suited data mining techniques in similar situations. In ideal projects, experience documentation also covers any reports written by individual project members during the project phases and tasks. CRISP DM was designed to provide guidance to data mining beginners and to provide a generic process model that can be specialized according to the needs of any particular industry or company. A competing model is the SEMA model. For SAS, data mining is an iterative process divided into 5 stages that are represented by the acronym SEMA. Beginning with a statistically representative sample of data, the SEMA methodology, which stands for Sample, Explore, Modify, Model, and Assess, makes it easy for business analysts to apply exploratory statistical and visualization techniques, select and transform the most significant predictive variables, model the variables to predict outcomes, and confirm a model's accuracy, argues SAS. The SEMA methodology is broken down into the following steps. Sample the data by creating one or more data tables. The sample should be big enough to contain the significant information, yet small enough to process quickly. Explore the data by searching for anticipated relationships, unanticipated trends, and anomalies in order to gain understanding and ideas. Modify the data by creating, selecting, and transforming the variables to focus the model selection process. Model the data by allowing the software to search automatically for a combination of data that reliably predicts a desired outcome. Assess the data by evaluating the usefulness and reliability of the findings from the data mining process. Projects that follow SEMA can sift through millions of records and reveal patterns that enable businesses to meet data mining objectives such as segmenting customers accurately into groups with similar buying patterns, profiling customers for individual relationship management, dramatically increasing response rates from direct mail campaigns, and understanding why customers are leaving for competitors. In the next section, I will discuss business intelligence, which refers to the tools, technologies, and practices that organizations use to gather, store, access, analyze, and visualize their data to make better informed business decisions. Business intelligence, or BI as it's acronymed, refers to the tools, technologies, and practices that organizations use to gather, store, access, and analyze data to make better informed business decisions. BI can also help organizations identify trends, spot opportunities and threats, and gain insight into their operations and markets. The term was first used in 1865 and was later adapted by Howard Dresner at Gartner to describe making better business decisions through searching, gathering, and analyzing the accumulated data saved within an organization. Large companies first embraced BI in the form of analyzing customer data systematically as a necessary step in making business decisions. BI uses a wide range of data sources, including structured, unstructured, and semi-structured data from databases, spreadsheets, documents, social streams, and web pages. Regarding BI, in its 2021 Magic Quadrant, Gartner claimed the definition of self-service is shifting in this field as augmented capabilities pervade platforms. At the same time, cloud ecosystems and alignment with productivity tools have become key selection factors. Gartner believes data visualization has now been commoditized and all BI vendors can build interactive KPI dashboards with common chart forms while drawing on a wide range of data sources. Augmented analytics is the differentiator, with machine learning and AI-assisted data preparation, insights generation, and insight explanation added to the platform to help business users and data analysts explore and analyze their data more effectively than users could do manually. BI tools are many and varied, and many of the largest software companies have data visualization tools, including Qlik, Tableau, Microsoft with Power BI, IBM with Cognos, Tibco with Spotfire, Domo, SAS with Visual Analytics, Amazon QuickSight, MicroStrategy, SAP, and some of the smaller players include Sisense, Yellowfin, Pyramid Analytics, Infor, Information Builders, and Alibaba Cloud. Gartner believes there are 12 critical capability areas when choosing a BI tool. These include security, includes user administration, auditing of platform access, and user authentication. Manageability, data usage should be able to track capabilities down to the level of how information is shared, including by whom and to whom. Cloud analytics, offering cloud option is important for today's BI tools. Data source connectivity, data comes in all shapes and sizes these days, so BI tools need to handle all types of data. Data preparation, support for drag and drop functionality from a combination of data sources as well as the creation of analytical models. Data cataloging, this needs to have sophisticated capabilities that will allow metadata collections. Automated insights, these should include augmented analytics as well. Data visualization, including highly interactive dashboards and deep data exploration. Data storytelling, combining interactive data visualization with narrative techniques to produce compelling, easily understood presentations. Natural language query, including both text and spoken querying capabilities. Natural language generation, users querying the data receive linguistically rich answers. And reporting, the ability to create and distribute pixel-perfect grid layout multi-page reports to users on a scheduled basis. Principles of data visualization. At its core, data visualization is a tool that transforms data into actionable insight by using it to tell a story. Data-driven storytelling is a powerful force as it takes stats and metrics and puts them into context through a narrative that everyone inside or outside of an organization can grasp. Dashboard design principles are most effective when they are part of a structured process. Dashboard-centric charts and visualizations fall into 4 primary categories: relationship, distribution, composition, and comparison. Modern dashboards are minimalist and clean. Flat design is the trend these days. By asking what kind of story you want to tell with your data and what message you want to convey to your audience, designers will be able to choose the right data visualization tools for their project or initiative. The human eye recognizes information visually rather than as blocks of data. Unlike computers, humans are at the mercy of their eyes' natural tendencies. The way humans perceive information is affected by several factors that contribute to how hierarchies are ranked according to the content within the layout. Factors affecting hierarchy include size, color, contrast, alignment, repetition, proximity, white space, and texture and style. With data storytelling, the following principles will help designers produce dashboards that convey meaning and tell the story they want to convey in the best possible way. Start at the end. Before putting any design elements in place, think about the end goal here. What are the most important elements that need to be showcased? Who's the audience? What is the context and device on which users will access the dashboards? Will the dashboard be viewed on the go or on an office PC? Or will it be projected as a presentation in front of a large audience? As Karamit Mangat explains in her article, dashboard layout must follow the design principles. The 4 primary types of dashboard include strategic, a dashboard focused on monitoring long-term company strategies by analyzing and benchmarking a wide range of critical trend-based information. Operational, a BI tool that monitors, measures, and manages processes or operations with a short or more immediate time scale. Analytical, these dashboards contain large streams of comprehensive data that allow analysts to drill down and extract insights that help operationally. Tactical, these information-rich dashboards are best suited for mid-management and help in formulating growth strategies based on trends, strengths, and weaknesses across multiple departments. Don't clutter. Dashboards have limited real estate to use, and one-size-fits-all isn't the practicing philosophy to use. When designers understand who the right targeted audience should be, designs, KPIs, Images and charts can be customized to display certain information for those specific audiences. Information shouldn't be crammed into the same page if it can be spread out. Designers need to think about their audience as a group of individuals who have different needs. A sales manager doesn't need to see the same information as a marketing specialist or a risk management clerk. Choose relevant key performance indicators, or KPIs. For compelling and effective dashboard design, it is essential to select the right KPIs for your business needs. KPIs help shape the direction of the dashboards, as these metrics will display visual representations of relevant insights based on specific areas of the business operation. Once the ultimate goal of the dashboard is determined and the target audience selected, choosing the best KPIs to feature in the dashboard should be simple. Context and layout will come later, but for now, focus on which KPIs are important and need to be emphasized, which take secondary consideration, and which can be dropped. Provide context. Numbers without context can be completely meaningless. It's impossible to know whether they are good or bad, typical or atypical. Without comparison values, dashboard numbers or KPIs are meaningless to a user, if not outright confusing. Designers should always try to provide the maximum information possible. Name all the axes, add titles where necessary. Comparison values can illuminate the meaning of a chart as well. For hierarchy, organize the information from most to least important. Headers should appear above the body text, and menus go at the top, bottom, left, or right of the screen. Keep it simple. Accessibility is one of the most important principles in dashboard design. Every design choice should be done to present the data in a clear and approachable manner that simplifies the decision-making process. Designers should ask questions like, what data does the user need? What information would help him or her to understand the current situation better? If you have two relative values, why not add a ratio that shows an increase or decrease to clarify the situation? Will providing last year's sales or last quarter's retention rate be helpful? Will adding an evolution ratio and a trend indicator augment the value of the dashboard's metrics, whether logistic KPIs or procurement, and thereby impress the user? This is the end of part 1. Please go to part 2 for the rest of this session. Business Intelligence Part 2. Choose layouts carefully. A visually well-organized dashboard helps users find information easily. Poor layouts force the user to think harder before understanding the point the designer is trying to convey. The general rule is that the key information should be displayed first on the top of the screen, upper left-hand corner. Start with the big picture. Major trends should be immediately visible. After this reveal, designers can proceed with more detailed charts. Group charts by theme with any comparable metrics placed side by side. The foundational 4 charts, bar chart, line chart, point charts like scatter plots and box plots, are great at indicating positional value, whereas dual axis charts are great at showing a direct comparison between two sets of vertical values, while also including the context of the horizontal axis. A heat map can be a good choice when there are a lot of data points to plot. However, the point density might make it difficult to see the true relationship between variables. So do choose your layouts and your charts carefully. Less is more. The Bauhausian concept that less is more, i.e., the notion that simplicity and clarity leads to good design, is a good motto to follow. Frames, backgrounds, effects, grid lines might be good options at one time or another, but there should always be a solid reason for their use. Also, designers should be careful with labels and/or legends, and they should pay attention to the font, size, and color, which should be big enough to be readable, but they shouldn't overwhelm any charts or visuals. Don't waste space on useless decorations. If customer information is being shown, then a picture of the patron can be useful for frontline staff, but back-end staff usually don't need an image of the customer. Be cautious with colors. Color use is one of the most important elements of dashboard design. Designers should stay as true to their company's identity as possible, using the same colors, logos, and fonts. Consistency is imperative, and using a limited palette is preferable. Designers should choose 2 or 3 colors and experiment with gradients. Limit the frequent use of highly saturated colors. Intense colors can draw a user's attention to a certain piece of data, but highly saturated colors in a dashboard can overwhelm the eye. Be consistent when it comes to color choices. Use the same color for matching items across all charts, and aim for complementary colors when displaying items in a sequence or a group. One final suggestion concerning colors: be mindful when using traffic light colors. For most people, red means stop or bad, and green represents good or go. This distinction can prove very useful when designing dashboards, but only when you use these colors accordingly. Color is also relative, and whereas a Western audience sees green as good, a Chinese audience sees red as good. Whatever color you do choose, approach with caution, as color can have deep semantic meaning for different audiences. Real time at the right time. Using real-time data can be a seductive proposition. Who doesn't want the latest information when making important business decisions? However, the cost often outweighs the value, and the results can be confusing. In some cases, this creates too much information, which can be distracting. Unless the business needs to track live results, most dashboards don't need data updated continuously. Real-time data serves to paint a picture of a general situation or a minute-by-minute trend. However, most project management dashboards only need to be updated periodically, and the considerable behind-the-scenes ETL work that needs to be done to constantly update real-time data isn't always worth it. The chart makes the dashboard. Asking the right questions will form the foundations for choosing the right types of visualization for your project, strategy, or business goal. The fundamental categories that differentiate these questions are based on the following types: relationship, distribution, composition, comparison of data. Choosing the right data visualization chart type is imperative. Information that displays clearly on one type of chart can be lost or muddied on another. It's important to understand what type of information you want to convey, and then choose a data visualization tool/chart that is suited to the task. Consistency is key. In terms of functionality, the main aim of a data dashboard is to give the user the ability to extract important information quickly. It's critical to make sure that the labeling and formatting is consistent across KPIs, tools, and metrics. If the formatting and/or labeling for related metrics or KPIs is wildly divergent, users will be confused, data analysis will be slowed, and the chances of making a mistake will increase. Use interactive elements. When considering what makes a good dashboard, factoring drill downs, pop-up windows, click to filter, and time interval widgets into the design is imperative. Drill down is a smart interactive feature that allows a user to deep dive into more comprehensive dashboard information related to an element, a variable, or a KPI without overcrowding the overall design. Another interactive element crucial in dissecting data is the click to filter option. This feature enables users to utilize the dimensions of the charts and graphs within a dashboard as temporary filter values. In practice, that means that this filter will apply data to the whole dashboard just by clicking on a specific place of interest. Looking at data over time is another crucial element to consider when designing a dashboard. A time interval widget will enable users to do just that. It allows users to enhance individual timescales on various charts, meaning users can easily look at their data across days, weeks, months, or even years. Double up your margins. White space, also referred to as negative space, is the area of blankness between elements featured on a dashboard design. Users aren't typically aware of the pivotal role that space plays in a visual composition, but designers pay a great deal of attention to it because when metrics, stats, and insights are unbalanced, they are difficult to digest. Designers should always double the margins surrounding the main elements of their dashboard to ensure each is framed with a balanced area of white space making the information much easier to absorb. Keep evolving. When designing dashboards, asking for feedback is essential. By requesting regular input from the users and asking the right questions, designers will be able to improve the layout, functionality, look, feel, and balance of KPIs to ensure optimum value at all times. Change is constant, and the principles of effective dashboards are dictated by a willingness to improve and enhance your design efforts continuously. A failure to do so will only hinder success. Overall, BI is an important part of modern business strategy, as it helps organizations make data-driven decisions and stay competitive in an increasingly data-driven world. Anyone who is interested in the BI tools click and tab below can check out the courses I have done on these subjects. The goal of BI is to help users gain insight and analysis from their data. Gartner sees a reckoning between two different platforms, the ABI and the data science and ML platforms, coming up in the not-too-distant future. On the one hand, ABI platforms perform augmented data science and ML tasks, with predictive models being executed behind the scenes and insights surfaced within the ABI process flow. On the other hand, data science and ML platforms increasingly feature enhanced data transformation and discovery capabilities, such as data visualization, that are traditionally more characteristics of the ABI platforms. Currently, the two platforms attract different buyers, but how long that continues remains to be seen. In the meantime, the power of these platforms put to shame the tools that were available just a few short years ago. In some ways, there's been a harmonic convergence of tools and their capabilities, with many of these ABI tools differentiating little from each other. And that might not be such a bad thing, because, as it always should, creativity will win out. The next section delves into analytics, and I will see you there. This is the source used in this section. One of the best illustrations of the four types of analytics is Gartner's Analytics Value Escalator, which first appeared in Gartner's Magic Quadrant for BI platforms in 2012. It breaks analytics down into four different types, each of which build upon the other. The four types are descriptive analytics, what happened; diagnostic analytics, why did it happen; predictive analytics, what will happen; and prescriptive analytics, how can we make it happen again. Another way to look at it is descriptive analytics gives you hindsight, diagnostics gives you insight, predictive gives you foresight, and prescriptive gives you amplified intelligence and automation. For example, descriptive analytics can be used with tools like Google Analytics to track things like website traffic, such as page views or number of visitors. With diagnostic analytics, you can mine browser data to figure out what caused a spike in website traffic over the past week, for example. With predictive analytics, you can build algorithms that will help you predict which customers might use a particular marketing offer. Prescriptive analytics will help you create algorithms for things like price optimization, i.e., selling a plane seat or a hotel room at the most profitable price. Descriptive analytics, or descriptive statistics as it's also known, is the study of past data. It is the first step in the data science process. It is the collecting, organizing, and analysis of data to identify patterns, trends, anomalies, and/or relationships in data between different variables to understand what has happened. Descriptive analytics is the process of summarizing and analyzing data in order to understand and describe the characteristics and patterns of the data. This type of analytics is often used to provide a snapshot or overview of the data, and can include techniques such as calculating statistics, generating visualizations, and conducting hypothesis tests. The goal of descriptive analytics is to provide a clear and concise summary of the data, and to identify key trends, patterns, and relationships that can be used to gain insight and make informed decisions. Unlike other forms of analytics such as diagnostics or predictive analytics, descriptive analytics does not attempt to explain or predict the cause or outcome of specific events, but rather focuses on summarizing and describing the data itself. Descriptive analytics helps us answer questions like, What was our sales performance last year? What were our top-selling products? Who are our best customers? Which areas of the country did we sell the most in? How many hours did each employee work last month? And how much money do we spend on marketing every quarter, year, month, or week? And while descriptive analytics explains why something happened, diagnostic analytics examines the data to reveal why something happened. It tries to identify the root cause of a problem, predict future performance, as well as recommend solutions. It is a subset of business intelligence, which encompasses all aspects of collecting, analyzing, and reporting on data to improve decision-making. With diagnostic analytics, you can use data and analysis to investigate and explain the causes of specific events or outcomes. It involves more in-depth and sophisticated analysis than descriptive analytics. It may include techniques such as regression analysis, machine learning, and data mining. It provides insights and explanations that can be used to improve performance, identify problems, or make decisions. The third step in the data science process, predictive analytics, could be dubbed the study of future data. Predictive analytics involves collecting, organizing, and analyzing past data to predict what will happen in the future based on a set of assumptions and rules defined by the user before running a model or an algorithm against it. Predictive modeling answers questions like, what are our best customers likely to buy next? Which products should we recommend to each customer? Which areas of the country should we focus on selling more products in? Which employees are more likely to quit next year? And where should a new store be opened up? In his seminal article, Predictive Analytics White Paper, Charles Nice states, predictive analytics is a broad term describing a variety of statistical and analytical techniques used to develop models that predict future events or behaviors. The form of these predictive models varies depending on the behavior or event that they are predicting. Most predictive models generate a score, a patron rating for example, with a higher score indicating a higher likelihood of the given behavior or event occurring. Predictive analytics can be used for customer relationship management, collection analysis, cross-selling, customer retention, direct marketing, flaw detection, fraud detection, product prediction, project risk management, and predictive pricing. Predictive analytics can use models like linear regression, discrete choice models, logistic regression, time series models, survival or duration analysis, classification and regression trees, multivariate adaptive regression splines, product prediction, neural networks, naive Bayes, and k-nearest neighbors. In his instrumental paper, Predictive Analytics, Wayne Erickson advises creating predictive models by using the following 6 steps. Define the business objectives and desired outcomes for the project, and then translate them into predictive analytic objectives and tasks. Explore and analyze the source data to determine the most appropriate data and model building approach, and then scope the effort. Prepare the data by selecting, extracting, and transforming the data, which will be the basis for the models. Build the models as well as test and validate them. Deploy the models by applying them to the business decision and processes. Manage and update the models accordingly. There are many use cases for predictive analytics, including retail and e-commerce companies can forecast demand for products and services. Healthcare organizations can identify patients at risk of developing certain medical conditions. Financial institutions can detect fraudulent transactions. Manufacturing companies can predict equipment failures as well as supply chain issues. Government agencies can forecast demand for public services such as transportation and emergency response. Telecommunication providers can forecast network usage as well as optimize network capacity. And transportation companies can predict demand and optimize logistical routes. Prescriptive analytics tries to optimize a key metrics such as profit by not only anticipating what will happen, but also when it will happen and why it is happening. In its Prescriptive Analytics Makes Waves with Retail and CGP, Profitect argues that predictive analytics differs from descriptive diagnostic and predictive analytics in that its output is a decision. It is the application of logic and mathematics to data to specify a preferred course of action. The most common examples are optimization methods, such as linear programming, decision analysis methods such as influence diagrams, and predictive analytics working in combination with rules. Use cases for predictive analytics include a utility company can optimize power plant operations and transmission networks to reduce costs and improve reliability. A manufacturing company can determine the most cost-effective production method. A financial institution can recommend investment portfolios to its customers based on their risk tolerance and financial goals. A sports team can use prescriptive analytics to determine the optimal lineup and strategy for a particular game based on player performance data as well as team dynamics. Prescriptive analytics takes predictive analytics one step further by providing actionable insights on how best to act on predicted outcomes in order to achieve desired goals or objectives. It provides guidance on which actions should be taken, when they should be taken, and why they should be taken, making it an invaluable tool for strategy, development, and optimization efforts. One of the things to note about the analytics value escalator is the x-axis is level of difficulty and the y-axis is value. The higher you go up on the slope, the more difficult it is to accomplish the analytics that you are aiming for. However, there is a corresponding value to that difficulty. Prescriptive analytics is the most difficult to accomplish, but it is also where companies can get the highest rate of return. These are the sources from this session. In the next session, I will break down the models available to you to analyze your data. Types of analytics include regression analysis, Monte Carlo simulation, factor analysis, cohort analysis, cluster analysis, time series analysis, decision trees, and A/B testing. Regression analysis is a statistical method used to analyze the relationship between one or more independent variables and a dependent variable. It is used to predict the value of the dependent variables based on the values of the independent variables. Common types include linear regression, multiple regression, and logistic regression. It is used in forecasting, time series modeling, and finding the causal effect relationship between variables. Monte Carlo simulation. This is a mathematical technique that uses random sampling to simulate the behavior of a system. It can be used to model a wide range of phenomena, such as financial markets, weather patterns, and physical systems. The technique is named after the Monte Carlo Casino in Monaco, where randomness is a key aspect of many games of chance. In a Monte Carlo simulation, a large number of random samples are generated and used to estimate the probability of different outcomes. This allows analysts to understand the range of possible outcomes and the likelihood of different outcomes occurring. Factor analysis. This is a statistical technique used to identify patterns of underlying relationships among a large number of variables. It is often used in the field of psychology to identify underlying factors or dimensions that may be driving a set of observed behaviors or attitudes. The technique is used to identify a small number of latent variables, called factors, that are believed to account for the relationships among the observed variables. The factors are typically created by considering the correlation between different variables and grouping the variables together in a way that maximizes the correlation between them. Cohort analysis. This is a statistical technique used to understand how different groups of individuals or cohorts behave over time. It is often used in fields such as marketing, healthcare, and finance to understand how different groups of customers, patients, or investors interact with a product or service over time. In cohort analysis, data is collected on individuals or groups of individuals, the cohorts, and is then grouped based on a common characteristic, such as when they signed up for a service or when they made their first purchase. The behavior of each cohort is then tracked over time, allowing for comparisons to be made between different groups. Cohort analysis can be used to identify patterns and trends in customer behavior, such as how long it takes for a customer to make a repeat purchase, or how likely a customer is to refer a friend. It can also be used to identify changes in customer behavior over time, such as how the behavior of customers who signed up for a service in the past year differs from that of customers who signed up 2 years ago. This can be useful in reducing customer churn. Cluster analysis. Also known as clustering, this is a technique used to group a set of objects in such a way that objects in the same group, called a cluster, are more similar to each other than to those in other groups, or clusters. Clustering is a way to segment the data into groups so that the observations within each cluster are more similar to each other than to observations in other clusters. There are different types of clustering methods, such as centroid-based clustering, e.g. k-means, where clusters are defined by their centroid or mean; hierarchical clustering, where clusters are built by merging or separating similar observations; density-based clustering, where clusters are defined by high-density regions in the data; and distribution-based clustering, where clusters are defined by a probabilistic model. The choice of clustering methods depends on the specific problem and the characteristics of the data. Clustering can be used in a wide range of fields, such as market segmentation, image processing, bioinformatics, and social network analysis. Clustering can be used to identify patterns and structure in the data, and can also be used as a pre-processing step for other techniques such as classification or anomaly detection. Time series analysis. Time series analysis is a statistical technique for analyzing and modeling time-dependent data. It involves identifying patterns and trends in data over time and using these patterns to forecast future values. Time series analysis is commonly used in fields such as finance, economics, engineering, and operations research. Techniques used in time series analysis include statistical modeling, signal processing, and machine learning. Decision tree is a graphical representation of a decision-making process. It is a tree-like model of decisions and their possible consequences, including chance event outcomes, resource costs, and utility. Decision trees are commonly used in operations research, specifically in decision analysis, to help identify a strategy most likely to reach a desired goal. In Section 2 of this course, in Sessions 2-07, 08, and 09, I'll lay out the analytical methods used in AI according to McKinsey in their article, Using Artificial Intelligence, McKinsey Maps 400+ AI Use Cases, Finds Trillions in Potential Value. It runs from descriptive analytics all the way up to reinforcement learning and transfer learning, with 12 types of analytics in between. In the rest of this session, I will discuss other types of analytics that are used that wouldn't be considered AI, machine learning, or deep learning. However, in some cases, analytical models that aren't considered AI, like decision trees, can be made into machine learning when they become decision tree learning. So welcome to the complexity of modeling when seen through the lens of AI. Other non-AI models include A/B testing, also known as split testing or bucket testing, is a method of comparing two versions of a web page, email, or app to determine which one performs better. The goal of A/B testing is to identify changes that will lead to an improvement in a desired metric, such as click-through rate or conversion rate. A/B testing is done by randomly dividing a sample of users into two groups, Group A and Group B. Group A will see version A of the web page or email, and Group B will see version B. The two versions are identical except for one variation that is being tested. For example, the color of the buy button, the position of the sign-up form, the headline, etc., etc. After a period of time, the results of the two groups are compared and the version that performed better is identified. A/B testing can be used to make data-driven decisions about website or app design, marketing campaigns, and product development. It allows businesses to optimize their websites and apps for maximum impact and improves their overall performance. Pros include allows you to make data-driven decisions by directly comparing the performance of different versions of a product or service. Can be used to test a wide range of elements from website design to product pricing to advertising. Allows you to optimize your product or service based on real-world performance rather than relying on assumptions or intuition. Robust algorithm that can handle large sets, missing values, and outliers well. Cons include requires a large sample size to produce statistically significant results, which can be difficult and time-consuming to achieve. Can be costly if it requires development resources or paid advertising. Can be prone to false positives or negatives if the test is not designed or executed correctly. Can be less useful when trying to test complex interactions or when there are multiple variables that interact with each other. Use cases include website design. A/B testing can be used to test different layouts, headlines, and calls to action on a website to see which version leads to more conversions. Email marketing, A/B testing can be used to test different subject lines, email layouts, and calls to action in order to determine which version leads to higher open and click-through rates. App design, A/B testing can be used to test different design elements, layouts, and features of an app to see which version leads to more engagement and retention. Time series model. The time series model is a statistical model that is used to analyze, forecast, or explain a series of data points collected over time. These data points are usually collected at regular intervals such as daily, weekly, or monthly, and are used to track a certain phenomenon such as stock prices, weather patterns, or economic indicators. Time series models are commonly used in areas such as economics, finance, and engineering. Pros: time series data often contains valuable information that can be used for prediction or forecasting. Many time series algorithms are designed specifically to handle the unique characteristics of time series data. Some time series algorithms, such as ARIMA, autoregressive integrated moving average, and exponential smoothing, have been widely used and studied in the field and have a strong theoretical foundation. They can take into account temporal dependencies and patterns in the data. Cons include data can be noisy, making it difficult to accurately model and predict future values, can be sensitive to the choice of parameters, which can make it difficult to achieve good performance without expert knowledge. The data may contain missing or corrupted data, which can make it difficult to use traditional time series algorithms. The data can also be affected by exogenous variables, which can be difficult to incorporate into prediction. Use cases include economic forecasting, financial forecasting, sales forecasting, weather forecasting, quality control, and social media trends. Survival or duration analysis. This is a statistical technique used to study the time until an event of interest occurs. This event is referred to as the failure or censoring event, and the time until it occurs is referred to as the survival or failure time. It answers questions like, what is the proportion of a population which will survive past a certain time? Of those that do survive, at what rate will they die? Can multiple causes of death or failure be taken into account? How do particular circumstances or characteristics increase or decrease the probability of survival? Survival analysis typically involves the use of survival functions and hazard functions to describe the probability of failure over time. The survival function, also known as the reliability function, gives the probability that a unit will survive beyond a certain time, while the hazard function gives the probability that a unit will fail at a given time, given that it has survived up to that time. The technique also accounts for censoring, which occurs when the failure time of some units is not observed. This can happen when a study is terminated before all units have failed, or when some units are still operating at the time of the study. Pros include allows for the analysis of time-to-event data, which can provide important insights into the factors that influence the duration of an event. Can be used to estimate the probability of an event occurring at a certain time, as well as the hazard rate, which represents the instantaneous risk of the event occurring. Allows for the use of non-parametric models. It can handle both continuous and categorical predictive variables. Cons include requires a large sample size to obtain accurate estimates of the survival function and hazard function. Can be sensitive to outliers and the presence of irrelevant variables. Requires that the event of interest is well defined and can be accurately measured. Does not provide a measure of how well the model is able to predict future events. Use cases include medical research, to analyze time to recovery, time to death, or time to recurrence of a disease. Engineering, to analyze time to failure of a product or a system. Economics, to analyze time to default or time to bankruptcy. And insurance, to analyze time to a claim. Here is the source to this session. In Section 2 of this course, in Sessions 2-07, 08, and 09, I'll lay out additional analytical methods that are used in AI.
If you're not a subscriber, click down below to subscribe so you get notified about similar videos we upload. To see the full course that this video came from, click over there. And click over there to see more videos from Simon Says It.